Alright, this is the first video from chapter 3 on the first two of Newton's three laws of motion. So in this video we'll do the first and the second law, and in another video we'll do Newton's third law. By the end of this video you should be able to solve this problem, shown right here, this example problem. Okay, so the first thing is Newton's first law of motion. And summed up very quickly, what this says is that if an object has no forces acting on it, then it will remain in motion. It will have a constant velocity. And remember, constant velocity also means the acceleration is zero. So those two things mean exactly the same thing. So this isn't, if you've never had physics before, this isn't automatically obvious. You throw a ball and nobody's touching it or anything. It looks like, it's just rolling around on the ground, and eventually it comes to rest. So it looks like nothing is acting on it, no forces are acting on it, and yet the velocity is going to change, right? The ball will eventually slow down and come to rest. So it actually took people a while to realize that this is true. And actually, what's going on in that example with the ball slowing down is that friction is the force that's changing the velocity. But if we're to remove the friction, then it would just keep rolling forever. Or maybe a better way to visualize this is if you're in space and you throw a ball, there's nothing slowing it down, in the absence of gravity or anything. So that ball is just going to keep moving away from you, and there's nothing to bring it towards you. Okay, so already we're using this word force, and your intuitive idea of what a force is probably fine for now. So a force is a push or a pull on an object. This is a vector. Force is a vector. So when you push or pull on something, you can push or pull on an object with a certain amount, a certain magnitude, and a certain direction. Remember, this is a telltale sign of a vector. So in 3D, you can have the direction be any, in any direction you want in those three dimensions. So force is a vector, and the SI units that we'll be using for vectors are newtons. So we'll see what the definition of a newton is when we talk about Newton's second law. But for now, you can just think of a newton as, a way of measuring force. And if you push or pull harder, then it's more newtons that you're pushing or pulling on an object. So we can measure it in this thing that we don't know quite yet how big 1 newton is. But if there's a push of 1 newton and then another push of 2 newtons, the 2 newton push is harder. Okay. Okay. So I think that's okay. So Shankar introduces the first law as the law of inertia. And related to this is what's called an inertial frame. So another definition I want to introduce. Inertial frame. So this statement right here, no forces means velocity is constant. Your book points out a scenario where actually this statement would not be true. So if you were in an airplane and you put a ball on the ground and the airplane accelerates, the plane takes off, then the ball is going to roll to the back of the plane. So from your reference frame, from your point of view, it looks like the ball starts to pick up speed towards the back of the plane. So even though there's no forces acting on the ball, friction is relatively small. You can imagine even if there was no friction, like if you had a perfectly ice, the aisle was all made of ice, and you had a completely slippery situation right there, like a hockey puck on the ice, it would still slide to the back, right? So it's not friction that's doing this. So this Newton's first law would not be true in that situation, in that airplane. So the reason that that's true is that the airplane is not an inertial frame. So right now this is going to sound kind of circular, but an inertial frame is a frame of reference. Remember we talked about reference frames before. Well, we talked about relative motion. So relative motion is motion with respect to a certain frame. An inertial frame is a frame where Newton's laws are true. So right now this probably seems circular. So actually for us, the way we can think of this is that an inertial frame is a non-accelerating frame. For us, this is a non-accelerating frame. So if we're on the ground, you know when you're in a car and you are accelerating to get onto the freeway. So you're aware sort of whether you're in an inertial frame or not. You know, are you pinned against something or not? In the case of the airplane, that's a non-inertial frame, so that the plane is actually accelerating. So your book talks about this a little bit, and it mentions that even if we're standing on the ground, we're actually on the Earth, and the Earth is revolving on its own axis. So in that sense, we're not in an inertial frame because we are accelerating, right? There has to be a centripetal acceleration pointing inward towards the center of the circle that we're going around. But it's actually pretty small. So your book points out that it's about 0.03 meters per second squared, which is small compared to the 9.8 meters per second squared we notice right away. So if you're on the surface of the Earth, we're not accelerating very strongly, so we can basically ignore the rotation of the Earth. But in these everyday experiments that we're thinking of. But maybe in some cases we can't ignore that acceleration. We have to take into account that we're in a non-accelerating frame. So we'll talk about that later when we talk about maybe the Coriolis force. So there are aspects to being in a non-inertial frame that we can explore as well. But yeah, just think of this, an inertial frame, as a non-accelerating frame. And those are the ones where Newton's laws are true. Okay, good. Okay, Newton's second law. So if you take Newton's first law, so let me remind you something about logic actually. If P implies Q, if a statement P implies that Q is true, this is the same. So logically, this is the same as if not Q, and that implies not P. Okay, so why am I bringing that up? So if we look at Newton's first law, if this implies this, then that means not this implies not this. So let's see what I mean by this. So this means that if this is not true, so if acceleration is non-zero, so Newton's first law is also implying, Newton's first law also says that if A is non-zero, then there must be a force, right? The opposite of no forces means a force. There has to be forces. So Newton's second law formalizes this a bit quantitatively. So it's the acceleration between acceleration and force. And the thing relating these two things is mass. Okay, so Newton's second law, it's the relationship between forces and acceleration. So there can be a whole bunch of pushes or pulls on an object, so we have to sum up all of the forces on an object. So you can say there's three forces on an object, F1, F2, F3. We have to sum them up. So all forces I. So we like to be kind of lazy in physics, so we might not write anything here and just say we're summing over I. So that means all of the forces that are acting on an object, sum them all up. This is called the net force. And when you add all of them up, add up all of these vectors, you get something relating to the acceleration. So Newton's second law says sum of all the forces on an object is mass times acceleration. And so you can see how this statement is implied by that. So if the acceleration is non-zero, if the right-hand side of this equation is non-zero, then the left-hand side is non-zero. And the only way for the left-hand side to be non-zero is for there to be a force, at least one force acting on an object. And when you add up all the forces acting on an object, they can't all cancel each other out. Right? There's one other definition, one last definition I want to bring up here. Well, let's see. Maybe I should point out, actually, first. I should talk a little bit more about mass, since we haven't talked about this yet. So M is mass. The SI units of mass are the kilogram. Not gram, but kilogram. So if you have if you have the mass of an object in grams, you have to convert it to kilograms. You know, a 60-gram object would have mass 0.060 kilograms. So SI units kilogram or kg. Now the definition of a kilogram, your book points out, we don't want to be very circular here and define the mass in terms of forces and accelerations. So the definition of a kilogram, you can think of it as just someone said that a piece of metal that has weight on Earth 2 pounds. So imagine a piece of metal that weighs about 2 pounds. You can probably imagine how much that is. Maybe the weight of a heavy textbook or something, a textbook. So imagine you have a piece of metal of this size. That's 1 kilogram. Now this is going to, once you have a kilogram, so someone defines a kilogram for you, this will help you define what a newton is. So given the mass, then you give a certain push or pull on this object and then measure its acceleration. And so what Newton's second law is saying is that the more you, so the force is going to, the bigger the force, the quicker the object is going to accelerate. Right? Another way of saying this is that if you have a given force, and this is what your book explores a little bit later on, 2 halves of the second law. If you have a given force, say by a spring that you stretch a certain amount, say you stretch a spring 1 centimeter, and then hook that up to something, that will pull on that object with a certain force. So suppose you do it over and over again, you get the same force. And the way you could ensure that is to hook it up to the same mass and measure the acceleration. So acceleration is something we're most familiar with out of all 3 of these things. Acceleration we know how to measure because we can track the positions of the object, we can track the changes in velocity, and we can track the changes in, track the changes in position, which will give us velocity, and then track the changes of velocity, which will give us acceleration. So we can measure acceleration by just taking a video of the object and seeing where the object is over time. So we can measure this. And then this will help us relate forces and masses. So say you give the same force to 2 different objects, you measure the accelerations, suppose an object doesn't accelerate as much. That's because it has a larger mass. So we can use the same force applied to different objects to measure their masses. Okay, so someone defines one of these things, just 1 kilogram, and then everything else we can measure relative to that, just by using Newton's second law. Okay. One other thing I wanted to mention, the last definitional sort of thing I want to mention is something that we're going to use over and over again. This is called a free body diagram. Free body diagram. So a definition of this is a diagram showing all distinct forces acting on an object. So for example, if you have a book resting on a table, then, and you don't have to get fancy, I can't draw anything really. You have a book, so you draw your object, and it can be as basic as you want. I mean, really, a lot of times we just draw a box. Like this is our book. You know, if you draw a person, maybe you could draw a silly stick figure or something. That's your object. So you have to have some object in mind. So in our case, we have the book, and then you draw all the forces acting on it. So we'll see that in this situation, you have two forces acting on it. You have the gravitational force downward. So if the book wasn't resting on the table and you just let it go in the middle of the air, it's not going to remain at rest, right? It's going to speed up in the downwards direction. So there's a gravitational force acting downward on it, on the book. But if it's resting on a table, there's also the table pushing up on it with some normal force. Right? So if the book is resting on the table, the two forces are going to be equal and opposite. The book resting on the table has acceleration 0. And from Newton's second law, if A is equal to 0, then the sum of the forces is 0. So I know that the forces in my free body diagram for the book, so this is the free body diagram for our book. Right? You draw the object and then draw all the forces acting on it. So they're going to be arrows in certain directions. And these two forces will cancel each other. So if we're using Newton's second law for this situation, it would be 0 equals 0. The sum is important. You can't just take one of the forces acting on the object. You have to sum them all up before you apply that formula. Okay. So I think we're ready. Your book is just talking a little bit. We're going to have a separate video where we go over springs in more detail. But this was the idea on the left here. This was the idea that you can use a spring to get a same force acting on several different objects. So this is a way of measuring mass, because you could chart out the acceleration and see, based on how quickly an object accelerates, what the mass is. So your book is just talking about that in a little bit more detail. And then your book is also mentioning that, so acceleration is going to say it's a second derivative of position with respect to time. So talking about one dimension in particular now. But maybe the force also depends on position. So this could be some function of x. So if you have a function of x is equal to the second derivative of x, you can set up a differential equation to solve for the motion of the object. So this is what Shankar means by a complete Newtonian problem. He just means that Newton's second law will tell you how the object is going to move over time, in particular its acceleration. And you can use that to see, well, what's the x position going to be at a short moment later. And then we'll have a new force, and then a new acceleration. So this just kind of keeps going back and forth. Okay, we're in a position now to answer our original question. All right, the box to the left is moving upwards with constant speed, 10 meters per second. So, original problem. The box is moving with constant speed. Right, so there were already two forces shown. Up, 10 newtons, and then down and left, 10 newtons. So it didn't say this on the original diagram, but let's say that's 45 degrees right there, just to make it quantitative. And then there's already a coordinate system set up too. So we can be particular about the direction of F3. Okay, so if the box is moving upwards at constant speed, the velocity doesn't really matter when it comes to Newton's second law. See how velocity doesn't appear in this formula right here. There's no v's here. All that matters is the acceleration. And so if the box is moving upward at constant speed, this means that the acceleration is 0. So that we just know from kinematics. And then combining this fact with Newton's second law, if the acceleration is 0, that means the sum of all the forces acting on the box has to equal 0. So if we call this F1, we call this F2, F3 has to be a force, so that F1 plus F2 plus F3 is 0. So what this means is that F3 is minus F1 plus F2. So if we add up F1 and F2, those two vectors, and then stick a minus sign in front, that'll give us our F3. Okay, so let's do that. So it looks like F1 is all in the, remember our coordinate system here, I hat and j hat. So it looks like F1 is all j hat. It's 10 newtons in the j hat direction. And then F2, so remember that this was 45 degrees with respect to either the horizontal or the vertical. So cosine of 45 degrees equals sine of 45 degrees equals about 0.71. So that times 10 newtons is about 7.1 newtons. Right? So this vector F2, which is pointing down and left, it has a negative I hat component, and a negative j hat component. F2 is approximately negative 7.1 newtons. Right? If we wanted to be exact, we could, and ignore any semblance of significant figures. We could say negative 10 over root 2 newtons. So we have that and negative 7.1 newtons j hat. So if we add these two, so F1 plus F2, looks like our I hat is negative 7.1. And then for j hat, it's 10 minus 7.1. It looks like that's 2.9, but positive, 2.9 j hat. So our F3 is minus that. Right, so in other words, F1 plus F2, it's pointing left and up a little bit. Right, the negative I hat is left, and this is a little bit upwards. But F3 is going to point down and right, because it needs to counteract these two things. Right, so F3 is actually going to point this way. Maybe a different color. F3 needs to point this way to counteract those two. So F3 is minus that. Looks like it's plus 7.1 newtons in the I hat direction. And then negative 2.9 in the j hat direction. This will be our answer for F3. Notice how the fact that the box moving upwards was irrelevant. It was the fact that it was constant speed. So we could have had the same problem, but the box moving downwards at constant speed would have been the same exact answer. The box could have been at rest, would have been the same exact answer. Remember, it's the dynamics that Newton's second law applies to, the fact that the acceleration is 0. And if F3 was not here, then this box would be accelerating in exactly this direction, the direction of F1 plus F2. So it'd be accelerating left and up. So if it started at rest, it would start moving in this direction. Okay, so we'll be continuing, so more on the spring force in a couple videos, but the next video we'll be talking about Newton's third law.